And finally, our last video about limiting reactant or reagent. It's our last video where this is the major topic, but we will continue to talk about it all semester, I promise. All right, a giant problem. Aspirin, aka acetylsalicylic acid, is synthesized by reacting this thing and that thing, by reacting salicylic acid, this thing, and acetic anhydride, that thing. Acetic acid is also one of the products. In one experiment, you start with this much of salicylic acid and that much acetic anhydride, and you have a bunch of questions to answer about it. What's the limiting reactant? How many grams of aspirin are you potentially going to make? How many moles of acetic acid might you make? How much of the excess reagent is left in grams? If the yield is 58%, how much aspirin was actually produced? That's a lot of questions about this same thing. So, step number one is always and forever write a balanced equation. So we start with acetylsalicylic acid. Sorry, we don't start with that. We start with salicylic acid and acetic anhydride, and we end up making acetylsalicylic acid and acetic acid. There's our equation. Is it balanced? 7 plus 4, that's 11. 9 plus 2, that's 11. 11 carbon on each side. 6 plus 6, that's 12. 8 plus 4, that's also 12. That's 12 hydrogen on each side. 3 plus 3, that's 6. 4 plus 2, that's 6. 6 oxygen on each side. Believe it or not, that is a balanced equation. 1 is the coefficient for everybody. Okay, so write a balanced chemical equation, and then we can start answering the questions. If we started based on what we've done previously, we could start with our amount, 95.23 grams of this guy, and go to moles of that guy, and then go to moles of aspirin, and then go to grams of aspirin. But that will actually only answer part A of the question, which is limiting, and maybe part B. But then we would have to do a lot more work to get to part C and D and E. So sometimes it's very helpful for students, instead of doing these long strings of math like this, we can fill out a table in order to help us organize some of our thoughts. Our table rows will be as follows: initial in terms of grams, initial in terms of moles, change and final in terms of X, and final moles and final grams. This is not an ICE table, an ICE box. If you remember your chemistry from high school pretty well, you might remember ICE tables. That's not what this is. Sometimes I might even call this a start-end table, because it's not an equilibrium process that we're talking about. It's a limiting reactant table. And you'll see, that's a reactant, you'll see that that means the way we calculate things later on is different from an equilibrium table. Okay, so we'll start by answering the question, what is limiting reactant? All right, again, this is a limiting reactant table that we're filling out. If we fill out our initial row of grams, that's not anything to do with math. That's just writing down what we've got. 95.23 grams of this, 100.7 grams of that, and none of my initial products. I don't have any product before the reaction begins. So then I need to convert this into moles, convert this guy into moles. I can set it up as 90.23 grams of that guy. So this guy in grams converted to moles. 1 mole of this guy weighs 138 grams. This time I actually rounded carbon to carbon 12 and hydrogen to hydrogen 1. But if you carried out more decimals here, that would probably be great. Do that division and you get 0.690 moles of this guy, which is salicylic acid. 0.690 moles. Do the exact same thing with this, 100.7 grams of this, times, or divided by, times 1 over the molar mass of that guy. 102 grams, again, carbon is 12, hydrogen is 1, oxygen is 16, according to the rounding that I did here. we get 9.87 moles of this thing. 9.87. This is super easy. It's 0 and 0 moles of those guys. So that was a simple conversion for these two numbers to get from grams to moles. And then here comes row X. That means how much do you gain or lose? So I'm going to say that I lose X amount from this. The reason I say I lose X amount is because there's a coefficient, an understood coefficient of 1 in front of here. So I lose 1x. I lose 1x. I gain 1x. I gain 1x. I'm going to be losing these at a rate of x and gaining those at a rate of x. Okay. My final, in terms of x, it really just means take this moles minus x and put it in as an equation. 0.690 minus x, 0.987 minus x, 0 plus x, 0 plus x. Yeah, I know, that's the same thing as just x. Yeah. So here's where the limiting reactant part comes in. You take your two sets of final, in terms of x, things, and set them both equal to 0. So over here, we've got 0.987 minus x equals 0. That means x would have to equal 0.987. If we set 0.690 minus x equal to 0, that means x would have to equal 0.690. So from these two equations down here, what I'm trying to figure out is which x is smaller, because the smaller x will tell me that reactant is limiting. And this x is smaller, therefore that's what x should actually equal, and that reactant is limiting. So x actually equals 0.690. So then I go back and fill in the rest of my table, filling in x as 0.690. That means 0 for that thing, minus 0.690, 0.297, plus 0.690, plus 0.690. Yeah, I'm filling in the smallest x for all of those x values, and that's how I get this final x in terms of moles. And then, finally, I take my number of moles and convert it to grams using molar mass. Well, 0 moles is obviously going to be the same as 0 grams. 0.297, you got to use the molar mass of that thing to get 30.29 grams, this one, and that one also. You should do all that math to the side to make sure that I'm doing it right. So, our questions from the beginning, if we revisit them, it was A through E, and question A was, what's the limiting reactant? The reason I put all this stuff in a table is it helps me organize my thoughts and sort of see a picture type view of where I'm at. The limiting reactant is obviously going to be this thing, because it has 0 moles in the final, 0 moles and 0 grams in the final row of my table. So salicylic acid is my limiting reactant. How many grams of aspirin are possible? Looking at my table, knowing that this is aspirin, I look at my final row and I see this many grams of aspirin are possible. Okay. How many moles of acetic acid are possible? If I know that this is acetic acid, then I look in my final mole column and I know that I can make that many moles of acetic acid. How much of the excess reagent is left in grams? Remember, this was my limiting reagent because there was 0 of it. This is my excess reagent. So there's 30.29 grams of my excess reagent left in grams. If the percent yield is 58, how much aspirin was actually produced? Why did I take us back to the table here? Because this is the amount of aspirin that you could produce if all went perfect. What's the name of that value? That's the theoretical yield. Theoretical. So 124.2 is the theoretical yield. But if the percent yield is 58, percent yield is actual over theoretical times 100. Percent yield is 58. Well, 124.2 is my theoretical according to the table I filled out. I can do a little solve, cross-multiply kind of thing here, and get that 72.04 grams of aspirin is what I actually produced out of this thing with a 58% yield. Yeah? That was faster work, in my opinion, than some of the other problems that we've done. I think that I like it because it breaks down your steps into smaller steps, and it makes your overall results much more visible, much more visual, easier to see, in my opinion. Can you do all limiting reactant problems as limiting reactant tables like we just went through? Yes. Can you do all limiting reactant problems as long strings of dimensional analysis unit stuff that we did for the previous 2 videos? Yes. Do I care which way you set it up? Not at all. I want you to get the answers right, and I want you to understand what you're doing. So do it in a way that you can understand what you're doing, and secondly, get the answers right, if at all possible. One more thing, let's talk. The reaction between aluminum and iron 3 oxide can generate temperatures approaching 3,000 degrees Celsius and is used in welding metals. This reaction produces aluminum 3 oxide and iron metal in one process. 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. What's the limiting reactant? How many grams of aluminum oxide are possible? How many moles of iron metal? What's the excess reagent? How much of the excess reagent is left in grams? Step number 1, write a balanced equation. So combing through the words, here's my equation, except it's not balanced. I've got 1 aluminum on the left and 2 aluminum on the right. So let's stick a 2 out there. 2 aluminum on the left, 2 aluminum on the right. 2 iron on the left, 2 iron on the right. 3 oxygens, 3 oxygens. Now it's balanced. So we could walk through this whole thing and say 124 grams of this and 601 grams of that, but we're not going to walk through the whole thing right now. The reason I bring it up is because this X row, you have to take into account coefficients. So you're going to lose 2X under your aluminum row. You're going to lose 1X under your iron 3 oxide row. You're going to gain 1X under your aluminum 3 oxide. You're going to gain 2X under your iron row. Those coefficients get carried down to your X values. So when you're setting each of your reactants equal to 0, don't forget that coefficient in front of your X because it matters a lot. That's the end of limiting reactant. Goodbye.